Okay, so I'm just telling you, J, the current density, is proportional to electric field. And that makes sense. If you get an electric field in a conductor, you got the electron cloud, it's going to accelerate the electrons, which then are going to bounce off of things and the cloud's going to drift. Okay, and we've seen that. So it makes a certain amount of sense intuitively, and when you measure it, it turns out to be so, that the current density is some constant multiple of the electric field within a wide range of electric fields, okay? And temperatures, okay? Temperature does have an effect on this proportionality constant. You know, at standard temperature, and it doesn't vary much around room temperature, okay? Yeah, you heat things up to 1,000 degrees, things change. Okay, so here are the three proportionality constants, and the units of the constants are such that if the electric field's in newtons per coulomb, the current density is in amps per square meter. So you get this, you're inside this conductor, you want to know how much current's flowing through some area. You just multiply that area by the current density and you get the current. So, example, 3 joules per coulomb, uniform 2 meter long wire, 2 meters, and 1 millimeter diameter. And I didn't specify nichrome, and I was going to specify it down here. Okay? Then this is what you have. So what's the electric field? Well, 3 joules per coulomb in a 2 meter wire means it takes 3 joules of energy to move through 2 meters. Okay? And if it's a uniform wire, there's a uniform force moving that thing through, so that uniform force multiplied by 2 meters had better equal 3 joules. So the force has to be 1.5 newtons. And if it's 3 joules for every coulomb, it's 1.5 newtons for every coulomb, because it takes 1.5 newtons acting through 2 meters gives you 3 joules. Very simple. What's J? Well, you come back to this. J is your proportionality constant times E. Now, E's in the direction of the wire, so I don't bother with a vector. But we know whatever the direction of the wire is, that's where the vector is going to be, right? Multiply this by a unit vector in the direction of the wire, you have the field. Okay, so here's J. It's this. And it's simple. Now, I didn't use units with the 1.5 because I didn't use units here. I used the fact that E is, if E's in newtons per coulomb, and 1.5 is the electric field in newtons per coulomb, and J's in amps per square meter, then J will be in amps per square meter when you multiply it by this constant. Okay? Now from that you can determine what the units of the proportionality constant are, and you need to do that, and I'm not going to tell you. Okay? You work that out. So anyhow, you multiply this by this, and it gives you the density in amps per square meter. You got 900,000 amps per square meter, almost 1 million amps per square meter. So if you have a square meter wire of nichrome with a 3 newton per coulomb, or 3 joule per coulomb potential difference over 2 meters, you're going to get almost 1 million amps. And if you build a rail gun, which you don't want to do with nichrome incidentally, but if you build a rail gun, you're going to need, a rail gun that'll shoot a projectile from here to Roanoke in 90 seconds, okay? Like the Chinese have in their, or don't know if they have them or are about to have them in their warships. You need like 1 million amps, millions of amps, which is an engineering problem, not a physics problem. Okay, anyhow, you get all those amps. Now, if you've got a smaller nichrome wire, 1 millimeter in diameter, well, you just multiply the number of amps you have per square meter by this cross-sectional area of the wire, and there's your current. 7/10 of an amp, which kind of makes sense. Okay? And then you ask what the units of the proportionality constant are.